Good afternoon. Welcome. I welcome all of you. Today, the first talk of this foundational course will be given by Shanchan Ball of second year BMAT, and the topic is motivation for group theory. Over to you, Shanchan.
Hello.
Just a thing. Please unmute yourself and ask questions, or just put the questions in the chat box, and otherwise mute yourself. Okay, Shanchan, start. You can begin.
Can you see my screen? Like, is it visible?
No.
Hello.
No.
It's
Not
not visible.
No, sir, not yet.
I have started it, but
But we can't see a screen.
then I'll stop here. Now?
No, sir.
Nope.
Still, it's not shown.
No.
Not at all.
Maybe I just go out and join again. Rahil, can you make me host or co-host?
Yeah, I have made you co-host. Yeah, now it is visible.
Yes, sir, now it is visible.
Have you uploaded the slides anywhere?
Hello. Is it visible now?
Yes.
Yes.
Okay.
Have you uploaded the slides anywhere?
No, not yet. Not yet. Okay, so hello everyone. So we are planning to do a lecture series on group theory. Today I would like to give an intuitive picture of groups, and then Rahil would continue with the rigorous structure. Firstly, groups are some algebraic structure. They are the fundamental part of modern algebra. They recur throughout the domain of science. The term group was coined by Galois, Évariste Galois. So being an abstract structure, it becomes a bit difficult for beginners to understand group. So in this lecture, we'll take a little easier path instead of going through the rigorous definition. Okay. So let's start. So for motivation, we'll carry out 3 set of experiments. So starting with a cube, and then a triangle with level nodes, and 6 balls. So I will take this cube and rotate it and about this center. So this is our first experiment. And the second one is I will rotate this triangle by 120 degree. So the 2 moves to the top, 1 to the right and 3 to the left. And I will do it again. And now 3 moves to the top, 2 in the right and 1 in the left. And I do it again, and the triangle comes back to the original position. Now I move to the case of 6 balls. So I swap the positions of the third and the 6th ball. Now I move the first ball to the second place, second ball to the fourth place, and the fourth one back to the first place. Now I do the same kind of operation again, like moving the first ball to the second place, second to the fourth, and fourth to the first. Now instead of carrying out this again, I swap the third and the 6th ball again, and this is the configuration now. Now if I take that second ball to the first ball to the second place and the second to the fourth, fourth to the first again, and I get back the original configuration. So why I am doing such experiments? So 2 questions pop up. The first one is what is common and what is the need of such experiments. So let's check out what is common. What I do is I carry out in such steps, and I label these steps as F1, F2, Fn. I call the whole step taken together as F. And what I observe is this is the initial position of the cube and this is the final position of the cube. So what I do is I apply F and I get the final position, and this initial structure is somewhat invariant under this transformation, that is this F. That is, we are taking some step, but this structure is invariant. And instead, this is true for not only this square, but also for the 6 balls and the triangle with level nodes. So there is some sort of symmetry in the object. So this is group theory is the study of symmetry. So now comes what's the need. Let's check out the needs. Now, where do we encounter symmetry? It's everywhere. So hence group theory can be used whenever we encounter some pattern or symmetry. The Rubik's cubes can be solved through group theory. Obviously, the solvers don't use because a 7-year-old can solve a Rubik's cube. And obviously, will not recommend using group theory for solving it fast. Just like if you drive a car, you don't need to bother about the mechanics. So here group theory applications come. And even in numbers, when we observe pattern, we can apply group theory. Elementary results can be easily proved through group theory. Another important thing is, like for quadratic, cubic, and biquadratic, we have explicit formulas for calculating the roots for polynomials. But there is no such formula for quintic or 6-degree polynomial or any general n degree greater than 5. So why is that? And in fact, you can't do that. Why you can't do that is proved through group theory. Again, there is application in physics. For example, we study conservation laws in physics. Why do we need conservation laws? So we need laws which are invariant under any circumstances. I can apply it here, I can apply it at space or anywhere. So again, group theory can be applied there. So these were some needs of group theory. So let's move on. So I now take 3 balls, just like we took 6 balls in the first slide. So instead of taking 6 balls, I am taking 3 balls to make it a bit easier. So I take these 3 balls, red, green, and blue, in order, and I keep it same. That is, I perform nothing. And I call this operation of performing nothing as I. Now I move the first ball to the second place, second ball to the third place, and the third ball to the first. Hence, now it will look like this: blue, red, and green. And I call this operation, whatever we are performing, as sigma. Now I take these three balls and I take this configuration and I apply sigma again. So now what happens? Now blue moves here, red moves here, and green moves here. So what we are doing, I am applying sigma twice. So I write it sigma square. Okay. Now if I apply sigma here again, green moves here, blue moves here, red moves here. And that is exactly same as the initial configuration. So I can write sigma 3 is I. Because if I do sigma thrice, it's basically same as doing nothing. So I'm not writing sigma 3 again because I've already written I. Now I do another operation, that is I swap the last two balls. So green moves here, blue moves here. So it becomes red, blue, and green. And I call this tau. Now if I do tau again, that is if I swap this, then I will again get back the original configuration. So I can say tau 2 equals. So I'm not writing tau square again. So what I do is I take this configuration, that is after the application of tau, I apply sigma to it. Now what happens? Red moves here, blue moves here, and green moves here. So I get something like this. And since I am applying tau first and then I am applying sigma, I name this sigma tau. So now the configuration becomes green, red, and blue. Now instead of applying tau first, I apply sigma first. So I get this configuration, and now I swap these two balls. Now what happens? Blue, green, and then red. So now I apply sigma first and then tau, so I call it tau sigma. Now, is there any other possible options left? No, because we already know there are only 6 possible permutations of 3 different balls. So all the possible operations have been listed. And I form a set of all these operations and we call it G. Now what does these operations do? This operation, when I apply it to this configuration, I get all these configurations. And this is nothing but permutations. Okay. Now let's list down the observations. In order to note our observation, what I do is I make a table. Now what does this table says? This table says that I apply these things first, whatever is written here, then I apply these things. And whatever I get, I write it down here. Now check one thing, if I do I, and then if I do any of these steps, I get back those steps again. Now this is trivial because I is basically doing nothing. And the opposite also, if I do any step and then if I do I get the same back. The another thing is, in each row and each column there is I. Now this means that if I take any action, any step, it can be reversed by another step, which is already listed in that set. So this is our second observation. The third observation is, whenever I perform any step and then another step from this step, I get a step which is already listed. Now in this case, it will be true obviously, because there are only 6 possible options and we have already listed the 6. So there can't be any other possible. So it should belong to that set. This is our third observation. And the fourth observation is the composition of steps, that is taking one step and then another step, is definite. Like if I do this sigma and then sigma tau, I will get tau. And that's like definite. It will not change. For example, if you do it any other time or anywhere else, you will always get this one, provided the definitions are same. So these were our observations. Let's write it down. So yeah, this is our observation. Composition is definite. Composition of two elements is again an element in G. Composition of identity with other elements is that element itself, and all the actions or all the steps are reversible. So these were our deductions. Hence we are ready, and now we can construct groups. So instead of writing down all those long rules, we can give the rules a particular name. The first rule is closure. Now what does closure states? If I take any element in G and another element in G, and if I compose them, then I get another element which is already listed in G, just like in the previous example. And the second rule is that I have not listed in the previous observations is associativity. Now what does this states? This states that if I compose B and C and then if I apply A, it's same as applying C first and then composing A and B and then apply. This is the general associativity that we have learned in juniors. And the third is existence of identity. This says that there is an element which does nothing. What does this mean? This means that if I do this element and then if I do another element, sorry, then if I do another step, then it's basically same as doing the second step itself. Similarly for opposite, like doing this step and then doing the step of doing nothing is same as doing this. This is the third rule. The fourth rule is existence of inverse. This means that all the actions or all the steps are reversible. So there is some element in G already listed which can
Sir,
reverse.
can you please explain A small o b? What does that function mean?
Sorry, there is no function here like this thing, this.
A map to B, yes, A composition B or something like that.
Means that I am taking this step, then I am doing this step. Like I am doing tau and then sigma. In whatever
Okay,
way.
sir. Okay. Means
Actually, I
performing
will
performing a certain operation.
kind of. I will tell you in a bit moment. Like it's not rigorous still because I'm just trying to give an intuitive picture. But I will tell you.
Okay, sir. Okay, sir. Okay, sir.
So you can see that 4 rules are listed, but still I have not listed one rule that's being definite. Now that is not a property of the group, that is rather a property of this thing. This is a binary operation. Now what does binary operation mean? This means we are relating two elements somehow, and that is definite. I am taking C, I am taking D, I'm mixing them somehow, and I get another thing, let's say E, which is definite. I'll always get E whenever I mix C and D. So group means a set G along with an operation. This tuple is together called a group, provided it follows all the 4 properties. then it forms a group. Henceforth, we could construct groups. Now, as we define groups, we move on to numbers to find groups among things that we already know. So we take integers and plus. Now, if I add two integers, I will get an integer. So it follows closure. It follows associativity because plus is associative. Now, there is an element which can reverse the addition. Like if I take 1, if I add a to it, I can reverse it by adding minus a, and I will get 1. So there is some element in integer which can reverse the addition of a, and this is for all integers. Yeah, sorry, I couldn't. Yeah.
Yes, in the case of integers, 0 is playing the role of 1, right? Identity element.
Yeah, exactly. Because if I add 0, it's basically doing nothing. Just like the I of the previously listed G. So this thing basically does nothing. Similarly, for rational numbers, for real numbers, and for complex numbers under addition. Now let's take irrational numbers. So let's take the first ring. So I have 1 plus root 2 and minus root 2. I add them, I get 1. And that is not an irrational number. So it's not closed. Hence, it doesn't form a group. Okay, so we are done with numbers, and now we will try to see groups. That is, we will try to draw groups. So I move on to the first slide experiment, that is the triangle with label nodes. Now I rotate this and I keep this configuration on my left hand side. And I label this arrow of by rotation. Like this arrow means I have rotated the triangle. So I rotate this again. So I'm basically rotating this. So I'll put an arrow here and I keep this configuration. Now if I rotate this, I will get back the original configuration. This one from where we started. Now if I flip this about this axis, so 2 moves to the right and 3 to the left, and I keep this here. Now I do this same for this thing and this triangle. And these are the possible configurations. And now from here to here, I go by a flip. So I label this with this red arrow. Now you can see that these red arrows have double arrows. Why is that? Because if I take this, I flip it again, I will get here. So it should be double. However, this is not true for this one, because if I rotate this, I will get this, not this one. So there is a single arrow right. Now you can see that there are blue arrows here. Why is that? Because if I rotate this in the same manner like this, then I will get to here. And if I rotate this, I will get to here. So instead of writing these triangles, I omit this triangle and I label these nodes with E, R, R square, F, R square, F, R, D. F means flip and R means rotation. R square means not the squaring. It just means that I am applied the rotation twice. This means that I have applied rotation twice and then I have applied flip. This means I have applied rotation 1 and this means I have applied rotation 1 along with the flip. This is just a flip. This diagram is known as Kelly diagram. And also that table that we have drawn in the observation is also known as Kelly multiplication table. Okay.
What is the name of this diagram?
Kelly diagram. So there are some Kelly diagrams here as an example. This is the Kelly diagram of S4, this is D4 and Z5. Now what is S4? So S4 is the permutation group of 4 elements. So in our one of the previous slides, we took 3 balls and we rearranged them somehow. So that formed a group. And instead of 3 balls, if we had taken 4 balls and then rearranged them, then we would have got a Kelly table, something like this. Sorry, Kelly diagram. And this is the D4, that is the dihedral group of 4. Just like we did it for the triangle in the previous slide, if we had started with a square with label nodes like 1, 2, 3, 4, and then if we would have drawn the Kelly diagram with rotation and flip, then we would have got this. And this is Z5 that I will discuss in a moment. So we take a n-sided polygon and label one of its vertex with this yellow dot. Now we rotate the n-gon, this n-gon, by 2 pi by n degree and keep this here. I rotate this again and again till I get back to the original configuration. And I give arrow here like this, and just like we did it for the triangle, only we have n-gon here, and I give it the same name as we have done for the triangle. ER dot 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 Rn minus 1 Rn is same as E because I'm doing it for an n-gon which has a regular n-gon rather by 2 pi by n. Now this thing is a group by itself. We don't need to flip it. Why? Because you can see it's closed, and again it follows associativity. Every action can be reversible. From here we can go here, and then we can go from here to here to get back to here. And there is a step which does not. So this forms a group, and this is known as the cyclic group or Zn. Why n? Because we have taken an n-gon. So in the previous slide I said Z5. So if we had taken pentagon, then we would have got Z5. So in the previous example, actually this n-gon is a 12 gon. So let's check one thing. So if we apply, I claim that if we apply any rotation 12 times, we will get back the original polygon. That is the polygon where 0 rotations have been applied. So let's check by applying R4 to this. So I apply R4 thrice. Apply thrice and I get back to here. So this means that if I apply it 12 times, I'll get back here. Why? Because 3 is a factor of 12. This shows that if I take any element and if I apply n times, I'll get back to the step of doing nothing. Now this is indeed true for all n and for any group. It's more general. If we repeat any of this process n times, we get back to the identity. Now I'm not proving this. Tahil would prove this in a rigorous way. I'm not proving this, but you can take it as a grain of salt. Okay, now consider ZP. And I start labeling each nodes with a number. I start with 0, and then 1, then 2, and this continues. Here I will get P minus 2, P minus 1. Here it will be P plus 1, P plus 2, and this continues. Now what I'm basically getting is all the numbers which are divisible by P here, all the numbers which leaves a remainder of 1 here when divided by P, remainder 2, remainder P minus 2, P minus 1. So instead of writing all those elements, I denote each set, whatever set we have got, it 0 bar, 1 bar, 2 bar, P minus 2 bar, P minus 2. Now we define addition in between these sets. What does addition of 1 bar and 2 bar means? It means that if I take an element from here, I take an element from here, I add them, and I see in which of these bars they belong. So I take, let's say, maybe anything, 1 bar and 2 bar, I will see that if I add this, I will get 3 bar. That is how we define addition. Now we will say that if I take, let's say I take p equals to 5 and I take 4 bar and 2 bar. Now if you follow my words, then you will get 1 bar. Because if it from 4 bar, let's take 4, from 2 bar, let's take 2, I add them 6, which gives a remainder of 1 when divided by 5. So it gives 1. So this forms a group again with the addition as we have defined, and 0 bar, 1 bar, 2 bar being the components of the group. Now, not only this forms a group, these also form a group. Now you will say that there is no identity here because I have removed the 0. But this time I use multiplication, not addition. Now again the question comes, what is multiplication? So multiplication is I take m bar, I take n bar, the same way as we have done it for addition. I take mn and divide it by p. Whatever remainder comes, I put it in r. M times m bar times n bar is r bar, where r is the remainder obtained by dividing remainder. And this should be non-zero, obviously, because this non-zero remainder, this is a non-zero divided by p. P is a prime. Now this forms a group. Now what did we learn in one of the previous slides? We learned that if I take this element, take any element, and if I do the operation p minus 1 times. Why p minus 1? Because that is the size of the group, p minus 1. P minus 1 times I get back to the identity. Now 1 is the identity. As you can see, if I multiply with this, it will get back these things. Now I can write this thing in a different way. Now a bar to the power p minus 1 now. P minus 1. What does this mean? This means that I take a to the power p minus 1 and then I divide it by p and I get a remainder of 1. That's nothing but the Fermat's little point. So this shows that how powerful group theory can be. In fact, you can prove the Euler's theorem also, a to the power 5 n equal to 1 mod n. There are also proofs of Wilson's theorem and so on. Many number theory results can be proved with group theory. So this group is also known as J star P. There is something called J star N also, not defining those here. Okay. Let's move on to subgroups. So I take this group. So just as we have subsets for sets, we have something called subgroups for groups. Now take this D3 here and look at this thing. Sorry for that. Just the outer part. Now this is nothing but Z3. Now Z3 is a group by itself, and also it is a subset of this group. So hence this is a subgroup of this. And it is denoted by this sign. Let's construct more groups from previously known groups. So I take this and I take this. Now what is this? This is Z3 and this is Z2. Now I move this Z3 to the middle and write it in a different fashion. Now I flatten these circles to ovals and I copy this here. Not only here, but here and here also. Now I remove these ovals and I copy those arrows also. So this is Z2 cross Z3 and this is also a group. Now you will say, what is the operation? Now the operation is, let's take A comma B. So as you can see, the elements are the elements of Cartesian product of two groups. They would be of the form like this. Now the question is, what is the operation? Now the operation is operating A and C in the first group, operating B and D in the second group, and then I'm putting this thing over here and this thing over here. Whatever I get, this is how we operate between this partition, these two elements of Z2 plus Z. And this is known as the direct product of groups. Even you can do for any groups, like G and H. Comes isomorphic groups. Now, as you can see, these two groups look exactly identical. Okay. Not only the nodes, but also the arrows. But I can say that this is S3 and this is D3. But these two look exactly same. So what's the difference? There's no difference actually, just I am renaming these elements. Like here we have sigma tau, here we have FR, we are somehow renaming them and I'm getting this D3. So this is also written with this symbol. Similarly, there are two more groups here. This is S4, let's say this is group of symmetries of a cube we have seen in the first line. But they are isomorphic. So hence we can study the rearrangement of four balls and we can get to know about the symmetries of the cube once we have established that they are isomorphic. Just like we have function for sets, we need a corresponding something sort of function for groups. So let us first take a function for groups from G to H. Now this should have interesting properties apart from just being a function, because group also has a operation structure in it. So let us take Z3 and Z6. First of all, I will move E1 to E2. That is, I will map E1 to E2. And then let's map A to, let's say, B square. Okay. This phi should have interesting properties, as I have already said. So this should preserve the group structure. That is, not only the arrow, not only the nodes should get mapped, but also the arrows should get mapped. That is, this arrow will, from the tail of the arrow will get mapped to here, and the head of the arrow will get mapped to here. So the arrow will be like this thing over here. Similarly, this arrow should go over here. Okay. Now this means that A square should go to B4 in order to conserve the group structure. B4, and now this arrow moves to here. So I'm putting a shadow of this thing in this image, putting a shadow of group G to H. And this function, which has some special properties, is known as homomorphism. Now let's take another example. So first of all, we connect E1 to E2, as we have already done. Then we map A to, let's say, B. Okay. So this arrow gets mapped to here. Similarly, this arrow should get mapped to here. This means A square should get mapped to B square. This means this arrow from A square to E1 should get mapped to this thing. Hence, E1, in order to preserve the group structure, E1 should move to B3. But that is not possible because phi has to be a function at first. So this shows that not all functions can be homomorphic. Now, what is the mathematics behind homomorphism? So what I do is let's take a part of the group. So I have X here, I apply Y here, so I get X star Y. Assume that phi maps X to phi of X. Now why should Y go? Y should go to phi of Y. This means I'm applying phi of Y to phi of X. This is phi of X dot phi of Y. And that is where X star Y should get mapped in order to conserve the group structure. So this means that phi is the function which follows this thing. Now this group operation and this group operation may not be same because these two are different groups. The sets may be different, their binary operations may be different. They may have completely different structures, but there is some sort of shadow from this group to that. Now another question comes: is isomorphism a homomorphism? Let's take two isomorphic groups, and I map each of the nodes. You can see not only the nodes have been mapped, also the arrows have been mapped. This shows that this is a homomorphism. And not only this is a homomorphism, but the function is bijective. This shows that any isomorphism is in any homomorphism which is bijective. So two groups are called isomorphic groups if there exists a isomorphism between two groups. Now let's see what is a symmetric group of a set. So symmetric group is the group of all permutations of the elements of set. For finite sets, it can be written like this: like let X be the finite set, and let N be the cardinality of this set. Then sim of X is isomorphic to Sn. Now this is trivial. Like I am permuting the elements of X, which X has n elements, so that is same as permuting n balls or n object. And X cannot have repetitions because X is a set. Now we define group action. A group G acts on a set X if there exists a homomorphism phi from G to sim of X. Now this seems to be a bit difficult definition, but this is an easy one. So let's understand with an example. So I take D3 and these three colored balls. So what this act means is that we will perform a permutation corresponding to each element of D3. So for D3, since D3 in construction of D3 we have already taken some steps, I take those steps in these three balls. That is, I rotate them again, and there exists some so there are some for corresponding to each element in D3, there are some permutation going on in between in these balls. Okay. Now let's take a non-trivial example. Instead of all different color balls, let us take one ball of red color and two of blue colors. Now let's perform the same set of actions. This is the action of doing nothing. This is the one time rotation. This is 2 times. And doing it 3 times, it brings back to the original rotation. And if I flip this, I get this again. If I flip this about this axis, then I get this thing again. And if I flip this about this axis, the red goes here and blue goes there, I get this thing. So what does action of a group means? It means that corresponding to every element of this group, there is some sort of permutation going on the set. So basically there is a switch here, which if I press, there is some sort of permutation going on. If I press this, there are some sort of permutations here. If I press this, some sort of permutations. Similarly for fr square fr. So this was in group actions. Now let's move on to another type of group, that is free groups. So in all the previous slides, we have seen that the steps or actions, whatever we have taken, was constrained. Now, what does constraint mean is, like we have taken sigma, the step sigma, and if I apply it thrice, sorry, I get identity. That is, I am constraining it. Like if I apply sigma, sigma square, sigma cube, and then I get back to original configuration again. And then if I apply sigma, so there's some of repetitions. Similarly for F, similarly for R, whatever we have done. So now what we will do, I will not constrain it. I'll take two steps, let's say A and B, whatever that step might be. I take that step and there is no constraint there. So they are free somehow. So I start from here, I go here, and then here, the B, A, B, and this continues. And I this from here also. So this is a group. So if there is a A, there should be A inverse. So there is some path returning here, some path returning here, or B. And there is a continuation going on and on. So this forms a fractal. So if I click this here, it continues. The same pattern repeats. So that's it. These are my references. So this is a really nice book by Nathan Carter, Visual Group Theory. This is also really fantastic book, but ultimately it goes to rigorous definition of groups. But this is completely devoted to visualizing group theory. This is a website which I may show you if we get time. And this is the future theorem. So this is a like nice theorem. You can check this out. The interesting part is that the theorem was discovered by a movie director. Actually, there was a cartoon show known as Futurama. In an episode called The Prisoner of Benda, two characters switch their minds through a special machine. So now the problem was that they cannot switch back. So what they did was they brought other persons as volunteers and switched with them multiple times. So the theorem proves that regardless of how many mind switches between two bodies are already taken, they can still all be restored to the original bodies using only two extra people, provided these two people had not had any mind switches prior. And its proof uses the permutation groups. Yes. Okay. That's it. Ask questions. And if there are no questions, then I may show you the group explorer.
Sir, can you explain DN again? The group.
Okay. So DN means just in the D3 case, we take triangle with level nodes 1, 2, 3. And I rotate this, I flip this. And similarly, in similar way, if we had taken an n regular polygon, and if I rotated it and flipped it, then I would have got dn. It should be something like this. I don't know if I'll be able to draw it. I may show you like it in Duplex. Let me show you some examples. There will be nodes here, and there will be a copy of this thing over here. There will be connections in similar way. There should be double-headed arrow here because flip is basically, if I flip it twice, then it brings back to the original. Yes.
Got it, sir.
So can we say in some sense that Sn is related to arranging n distinct objects in a line, while Dn can be thought of arranging n distinct objects in a round table or in a necklace, something like that?
Not always, because there will be more, I guess, more such permutations in round table, because In case of 3, it will be true, but for 4, I guess it will not be true. C4. I guess you can't do all the configurations because for round table there will be 3 factorial 6 thing, and for D4 has how many elements? 8 elements. There are more, I guess. If I'm right, I guess I don't remember this thing. Maybe I'm wrong. But I guess it will not be. For SN, yes, it is like it is rearranged in a line. Okay, then if there are no more questions, then I will show you that thing. Just a minute. Can you see my screen?
Yes, sir.
So let's see examples. So someone is asking Dn. So let's take an example of D5. This is how D5 will look. Yeah, this is nice. You can see it has been rotated.
How is D5
And-
defined?
Sorry?
What is the
Sorry.
definition of D5?
D5 is like taking pentagon.
Okay.
Sorry, I couldn't get you.
Got it. Thanks.
Okay. So this is I've taken a pentagon. I flipped it like this red arrow defines flip, and this green arrow defines. That is what it. Let's see some more examples. Let's take these things at 2 cross Z6. This is this. This is how it will look. You can more complex, like this has been done thrice. I've done Z2 cross Z4, then with that I have crossed with Z2. Let's take this one. 4 times. This will be a lot complex. These are the subgroups, many subgroups. This is D9 here. Here's S3 cross Z4. This is a lot complicated. You can just play around with this. This is a nice website. It gives the Cayley tables also, like multiplication table of S3 cross Z. And we have the object of symmetries also for let's see Z5. For Z5, there is a pentagon. Instead of taking pentagon, they have written like this. Again D4. So that's it then. Here, if you have any more questions, you may unmute yourself and ask. Put it in the chat box.
Sir, in the second column of Group Explorer, what was it showing within two less than greater than?
Two less than greater than. Oh, that's the definition. I'll show you.
So can you explain that notation?
Yeah. Just a minute.
Sir, your screen can't be seen.
Oh, it can be seen. Okay. Is it
Now it
visible?
can be seen.
Yeah.
Yes, sir.
So let's take Z4, for example. So there is something called generator of a group. So let's take Z4. So what are the elements of Z4? R square. We have taken R here. They have taken E here. So 1, R square, R cube. So there is an element R, which raised to the power 4 is 1. And if we know this, then we can construct a group, because if A is there, then A square should be there by closure, A cube should be there, and 1 should obviously be there in order to make it group. Now, once we know F4 is 1, then I will again repeat this process. So as you can see, here is one generator, and here there is two generators. Just like we have taken sigma and tau, here they have taken A and B. There can be more generators like A, B, C here. Now, once we have constrained it, we are. This is the constraint I am speaking about. I was speaking about in the free groups, because if we don't constrain it, then we'll get that fractal structure. Is it okay? Was I clear?
Yes, sir. So essentially, this means that this is all the groups with containing A with this constraint.
Yeah, and ultimately you will get one group only. Not like, even if you get more groups, they will all be isomorphic. Like instead of A, if you had taken R, you may say that I am getting a different group, but it's basically same as Z. Just you are renaming it.
Got it, sir. Thank you.
What is the definition of the group V4?
Okay, so this is the Klein for group. So I'm not saying this. This is defined like this only. So you can draw the Kelly diagram with these constraints, but I don't know if there is a visual interpretation of this. Let me check it out. There may be some. I don't know. This is the group in the Kelly diagram. Once you know this, then you can start drawing the Kelly diagram. Once you know this, because you'll draw A, then you'll draw A square from it, and it will continue.
What's the difference between visual group theory and like normal group theory?
No,
Because there
there's-
are different books on the same.
Yeah, but actually there's no different. This is like a different approach. Nothing difference, because ultimately group definition is that only, that what I have said, because that's how we study group theory. Now, why we give up the intuition? Because once we have defined the rigorous structure, then we can like go to autopilot mode and just continue doing problems. But when we have intuition, the problem is that maybe the intuition says something, it may be wrong. But once we have the rigorous definition, we can just go in an autopilot mode and do the problems with under the rules that we have defined. That's why we in mathematics we always try to define things and do it in a rigorous manner.
And what are cycle graphs?
I don't know this thing. I don't know. I even don't know. Maybe you can check it out. I don't know.
Okay, so we are here for next 5 to 10 minutes. or if you don't have any questions, then after maybe 5 minutes, we will close the meeting.
Sir, group is usually held over some set and one operation
Yeah,
with the conditions.
four
But
rules.
sir,
Yeah.
if the Kelly can we actually for any demonstration purpose or examination purpose, can we actually draw the Kelly diagram of something, or we usually resort to the Kelly tables?
Actually, we do, as I told, that Cayley table, the way we took in the lecture was intuitive idea. Basically, I never defined Cayley diagram in a rigorous. So
Yes.
whenever it comes to exams or whenever it comes to like solving problems, we always prefer the rigorous definition, because once we have the rigorous definition in hand, we are constrained by the mathematics of it. So we can never be wrong, but intuition may be wrong.
Hmm.
So,
Okay. Okay, groups are applied in the beginning of set. Groups are applied in various places,
yeah.
like in physics. And, so, in what kind of things actually we do in groups at the basic science level or at engineering level, in the undergraduate level, wherever we study, be it biology, engineering course.
in applications can be found in like solving polynomials, like finding roots of polynomials. You can prove those things. You can prove interesting things, like for example, if you can bisect an angle with a straight edge and a compass, but you cannot trisect an angle with a straight edge and a compass. In fact, this can be proved, and this can be proved with group theory. These are some small applications. Obviously, there are larger applications.
Okay, sir. Okay, sir.
Sir, one thing, can you open Group Explorer 1 second?
Yeah. Is it
Sir,
visible?
yes, sir, it is visible. In Z2 cross Z4,
Cross Z4, yeah.
yes, sir, how do we get this constraint AB equal to BA?
AB equals BA.
And
So
what is the
Z-
operation here? Because A is one operation in one Z2, B is in Z4. Then what? I mean, AB.
Like,
What operation is here? A
like
operation B.
what are the elements of Z2 cross Z? Which are the elements of the Cartesian product of these two sets? Right?
Yes.
So now this A is basically 1 comma R, okay, where R is from Z2, okay, and this B is basically 1 comma, let's say R dash, where R dash is Z4.
Yes, sir.
So what does B4 means? B4 means that I am taking, let me write this.
So that part I get, but what is AB equal to, I mean, AB equal to BA, that statement I cannot understand.
Let me write it.
Okay, yes, sir.
I write A as R comma 1, B as 1 comma r dash. Now r dash is from Z4 and is from, sorry, r is from Z2. So if I like perform r1 r comma 1 times 1 comma r1 r dash, it's like r comma 1 like 1 comma r dash. Now what's this mean? This means I will operate these two, that is r, and I'll operate this two, is r dash. And if I do this in the opposite side, that 1 comma r dash times r comma 1, this means I will operate this two, that is r, then I will operate this two. As you can see, these two are equal. So AB is same as BA.
Got it, sir. Thank you so much.
Okay, so if there is no question, let us end it here.